Okay, so yeah, thanks thanks for the introduction, and yeah, thanks for the opportunity to talk here. Would have been nice to get there in person, but I couldn't resist the opportunity of giving a talk at 11 at night from New Zealand. So before I start, I'd like to thank so my PhD student Nico, who should be somewhere in the audience in person, and also the funding agencies, so the Antarctic Science Platform, Deep South Challenge, and the Marsden Fund. And so I'll get straight to the point about what message I really want to convey here, and is that we have evidence at this stage that a log-normal distribution is better suited to characterize the flow size distribution in the marginalized zone than a power law. Okay, the power law has been well accepted as describing this flow size distribution from any data set, but we believe that the log-normal would do a better job. That said, I just want to introduce a few caveats here already, okay? First, I want to say that what I'm going to say only applies to a flow size distribution generated by repeated fragmentation. So, for example, from waves, okay? And also within a range of sizes from order of 1 to 100 meters. And of course, it requires a sufficiently large sample size as well. And it's unlikely to describe all observational data sets. All right, so here we are simply offering an alternative to the community to better describe, in some cases at least, the flow size distribution. So here the key message is that next time you analyze flow size data, consider trying at least to fit a log-normal distribution to it, and you might get surprised. So just going back to some fundamentals here, by flow size distribution, of course, I mean the probability density function associated with flow size L in a given sample. And it's obtained in 2 steps usually. So there is an analysis of aerial images where individual flows with a certain resolution are selected. And then from that, the typical way of plotting, extracting the distribution is to plot the cumulative distribution. And when plotting this cumulative distribution on a log-log scale, well, it seems like it's well approximated by a straight line or a couple of straight lines. So a power law or a variation of a power law, such as the split power law or the truncated power law, has been usually used to describe the flow size distribution. And that's from the very first measurements of the flow size distribution by Rothrock and Sondike in the early 80s. And so the power law can be formulated in this form here, of course, so it's proportional to the power of the flow size, and actually it can be understood as emerging from a theoretical fragmentation argument here, and the way it works is if you take a flow, so here it's an idealized rectangular flow, and you break it into n equal pieces. So here it's shown as being broken into 4 equal pieces, but it's not limited to 4. And it's done here with a probability p. And the other thing here in this theory is that if a flow is not broken at a step, then no further fragmentation of that flow occurs. Okay, so only the flows that get fragmented will experience further fragmentations. So if you do that, then you have scale invariance, which appears, and that results in a power law of the size distribution of the fragments. And the power itself here can be shown to be between bounded by 0 and 2. Now looking at observations, so there is this nice analysis here done by Stern et al. In 2018, looking at the range of exponents that were seen in the literature in many different observational data sets. And roughly they found that this power gamma was bounded between 0.5 and 3. So that's already a little bit outside the bounds of what the fragmentation theory I mentioned in the previous slide seems to say. And in addition, they offer some, well, they talk about the limitations in many of these analyses because so the quantity that is analyzed is the cumulative distribution as opposed to the probability density functions. And it is usually also done using a least square fit, which has a strong bias to it, instead of a maximum likelihood estimate, which is more robust. And often the goodness of fit is also not estimated. So that said, so there is clearly a lot of observation that that showed that it seems there is a nice relationship, a power law relationship between for describing the flow size, but in some other more controlled experiments and in also a few modeling studies, we don't seem to find that the power law holds. And so the question, of course, is why? And here are a couple examples of what I'm trying to say. And we've seen some of these earlier today, actually. So here are a couple of results from lab experiments. So these are flow size distribution obtained by wave breaking in the lab. You recognize the one on the right here, which was talked about by Luc earlier today. And on the left is an experiment which was led by Agnieszka Herman, who also talked just before the break. And they find a little bit different results here. So on the right here, you can see that the power law clearly doesn't hold because there is a mode. And actually the distributions which were fitted to those density functions were a Weibull distribution, I believe. And on the left here, so Herman et al. Had the idea of actually decomposing the distribution into two components. So one was a tapered power law or gamma distribution. So that's the blue curve here on the left. And then you have also a Gaussian distribution. So that's the red one. And then the distribution, the total distribution will be the sum of these two. Now, the reason for using this power law here is that it's been well known to describe the fragment size distribution caused by like explosions events, for example, or collisional events, where a lot of fragments are created at the same time. So that makes sense to describe those for small flows. But then it seems there is a mode here as well, which is why they use the Gaussian distribution. So here are some field experiments by Dumas, Lefebvre, and Dumont. And again, so here they actually, it's in the field, but they were able to control the breakup conditions by having a ship go along the ice edge to create waves. And then they were able to observe the breakup. And what they find here is these density functions here for the flow size, which clearly are not represented by a power law because, again, there is a mode somewhere here. And here are some modeling results. So that's a study that Vernon and I did a few years ago, where we set up an ice field made of circular flows in this case, and then we sent a wave through, and then we computed the stress field across all the flows, and then we had a breakup criterion, and depending on whether the stress field was strong enough to break the flows, then we redistributed the flows in the marginalized zone, and then we just keep doing that iteratively. And what we found here is that, again, the distributions are model. So there is a clear mode here for medium range flow size. So again, no power law. So what seems to be here a clear observations from these repeated fragmentation events here, which are seen in the labs or in the field or in the models, is that there is a mode which needs to be approximated somehow. and in particular when it's caused by wave breakup. So what we did here, and I should really put all the work. I should acknowledge that all this work's been done by Nico. And so what he did is set up a 2D model. So it's basically a simplified version of the model we did a few years ago with Vernon, where now the ice is invariant along the y directions here, and waves are essentially able to only propagate in one direction. And we use linear wave theory, and then we model the ice sheet here using viscoelastic ice covers, very similar model to the one Luc talked about earlier. We had this Robinson and Palmer damping as well, which he talked about. And then essentially what we look at is a multiple reflection transmission by a large array of flows. And so the idea is to use the amplitude, the wave period and phase of the wave field to force the system, and once we get that, we're able to derive a strain field throughout the ice. And then we run a simulations where we start with one semi-infinite flow, and then send the wave field through. And if the strain at a point is larger than a critical value, critical strain, then the flow breaks at that point. And then we just update the geometry and we keep doing that for many, many different iterations. So here, the breakup criterion, we used some well-established values from the literature here, sort of the order of 10 to the minus 5. And so one limitation of the model here is that we assume at each iteration, a flow can break only at one location, okay, but multiple flows can break in one iteration. Okay, and what we find are these distributions, okay, and here I'm just selecting a sample of the results we got, okay. You can read more about these results in the paper cited below, which was just recently accepted in Cryosphere, but this is clearly not a power law that we obtain, okay. We obtained this nice mode, and what we were able to find is that actually a log-normal distribution fits extremely well. And that is very consistent for a range of parameters. So we run many sensitivity tests and showed that this log normal seems to really consistently emerge. All right. So for more details here, I'll refer you to Nico's poster, who I believe the poster session for you was yesterday. And here is his poster. So I hope you had a chance to look at it, or if not, maybe you can still look at it. I'm not sure, but Nico will sure have more to say about this model than I do. All right. So what about the data? Well, so I showed earlier that there are many analyses which have shown that the power law does a good job. So what we did here is try to get our hands on some data. Which was actually not that easy to do for some reasons. But so here's one data set that we first had a look at. So it was first analyzed by Liu et al. In 2007. And it's the results based on a single image here, 2000 by 200 meters, which contain 2,344 flows. And the flow size here, which was estimated using the mean caliper diameter, ranged from 2.3 to about 90 meters. All right, and here's our results when we try to fit a range of different distributions. So at the top here, you see the density function, and at the bottom, it is a cumulative distribution. And you can see that the modes that we observed in the density functions here at the top really gets shadowed when we look at the cumulative distribution down below. So even though it could possibly make sense to fit so a Pareto distribution, that is a power law distribution, for a cumulative distribution, when you look at the density, it really does not, because the mode is not captured here. And so we fitted a log normal, and that's the green curve, and it does a fairly good job here when you look at the density. Now, it's still interesting to look at the cumulative distribution, because you can see that our fit doesn't do a really good job for large flow sizes, okay? And that's not very clear why. I mean, one possibility would be that it was just one image, and therefore large flows, well, could have been, you know, truncated essentially by the boundaries of the image and therefore not taken into account, which is why we may be over predicting them. But clearly, so the log normal is able to catch up the modes here, which is quite interesting and consistent with the findings from our simulation study. And here I'm going to show you further results, which I've only seen for the first time a couple of days ago. So again, Nico has all the was really claiming that work here, but so he managed to get his hand on more data, and I will leave to him for the details, to explain the details here of each of the experiments. But again, here we compared so the log normal and the Pareto or power law distribution, and again looking at the density function, the power law seems to do a reasonable job. So we claim here that the log normal outperforms the power law. You know, there may be other distributions which are well adapted, but at least comparing these two, it seems clear that that the log normal seems to outperform the power law. So there's more data set to look at. So if you have a data set you want us to look at, then please get in touch with us. That would be great. So again, I refer you to Nico's poster here for more details, or even have a chance to talk to him. Okay, so the thing is, with the power law, like I mentioned earlier, there was, well, I talked about this repeated fragmentation process here, which gave rise to self-similarity and therefore could explain the power law. So what about the log normal? Is there a similar kind of process which leads to a log normal? And the answer is actually yes, and it's not new at all. So that's referred to Karmograph fragmentation theory from the 1940s here. And the idea is that it really goes as follows. So if you consider a flow of initial size d nodes here, then what you do is just break it, so not at in equal pieces, but here just at a random point, okay? So we just sample a random point here, f node from 0, 1. It doesn't have to be uniformly distributed. It can be any other distributions with support 0, 1. But we create a new flow of size d1 by just multiplying f node with d node. And then we just repeat the same thing. So now we break d1, okay, and we obtain d2, and then after n step, then we had dn, which is related to dn minus 1, but then it's also related to d node by just multiplying all the f's together. And so the last step is just to say that, well, if you take the log on both sides now, then on the right-hand side you have, so the log of a product becomes a sum of logs, okay, which is the sum of random variables, which are, so using the central limit theorem, this is normally distributed. Since the log of the size is normally distributed, then the size itself is log normally distributed. So that's the key argument here. Okay, so what about the standard theoretical framework, here referring to Horvath and Zipperman, which has now been implemented as well in sea ice models of evolving the flow size distributions. So this is based on the standard transport equations here, which evolves the flow size distribution based on the velocity field and some source terms, which can be represent, for example, the breakup caused by waves. Can we somehow fit into this framework here the emergence of the log normal distributions? So that's really the question that I was wondering about, and to get there, actually, we can do that by looking at a stochastic process, and in particular, in this case, is a geometric Brownian motion, which does the job. And here we think of flow size L at a time t as a random process. And the assumptions we start making is that it evolves according to this ordinary differential equations. But the key part here is that K, the decay rate in this case, not only depends on time, but it's a random parameter. Okay, and here we decompose it as A plus B eta of t, where eta is the random Gaussian noise. And then we can use the tools of stochastic calculus essentially to show that the probability density function associated with the random variable LT is a time evolving log normal distribution, and it looks like that. So that seems, again, well, that we are able to generate a log normal distributions from a random fragmentation type process. But this log normal distributions here, it can be shown again to satisfy this so-called Fokker-Planck equation, which is the equations that govern the probability density function of a random variable, which is determined from a random stochastic process. And the idea is that, well, on the left-hand side, you can see this is the rate of change here with respect to time of the flow size distribution. So it seems to be similar to what the FSD evolution theory is. And just on the right-hand side, now you have a couple of operators which involve derivative with respect to flow size. And I guess the open question now is that, could we somehow integrate those into the standard framework for modeling the flow size distribution? And I'm not sure yet, okay? And there's a lot of work that could be done here to potentially do that. And one of the key question, of course, is the parameters that I defined here for the geometric Brownian motion would have to somehow be related to the underlying physics, okay? And that is not clear at all how to do that at this stage. But I believe it's promising, and something similar has actually been done in modeling the ice thickness distribution fairly recently. So yeah, we'll have a look at seeing if we can actually do something similar for the flow size distribution. All right, so just wrapping up here. So our claim is that the log normal distribution is better suited than the power law to describe the flow size distribution when it's caused by a repeated fragmentation. So for example, in response to a wave event. We've seen that by running simulations of a deterministic hydroelastic linear models. So that's the work done by Nico. We've also looked at some data, and the ones we have looked at so far are fairly promising, but clearly there's more to do. And also we see that it is a result of a fairly simplified stochastic process. There's a lot of that we don't know yet, and a lot of questions to answer. So in particular, we want to analyze more data sets and see if the extent to which it holds, okay, and we don't expect it to hold forever, especially if when we go to very large flow sizes, it may end up not being appropriate, or even very, very small flow sizes. And of course, there is the question of how to parameterize a source term in a FSD evolving equation here that would generate such a distribution. So still a lot of work to be done, but that's what we have so far. And here's the couple of papers that tells this story. So the one at the top here was led by Nico, was just recently accepted in the cryosphere, and that's if you want to learn more, then please talk to him about it. And yeah, thank you.
Questions? Are there any questions?
Thank you, Fabien, for a lovely talk. Okay, so you really want a log normal distribution, and you're finding ways in which that can be justified. Fine, and I would argue from observations it's log normal as well. That's fine. The Karmograph theory you described, where a flow breaks along some random point along its length, where that random point is a uniform distribution between anywhere along its length. have to say it does strike me as being physically quite unrealistic.
It's not. It doesn't have to be uniform. I said I didn't say. I said it doesn't have to be uniform. You can choose any distribution.
So okay, so that was actually my question. If the flow could break at some random point along its length given by some distribution which perhaps had its peak at halfway along its distribution, would that still lead in the analysis to a log-normal distribution? Okay, that's the important point. Okay, thanks.
Yes.
Are there any
Just
other
to clarify,
questions?
I don't. So sorry. Just to clarify, I don't really want a log-normal distribution. I think that's where the evidence has taken us. That's the way I'm thinking about it. But I'm happy to be disproved.
So we'll make a note of that. He's against all log normal distributions. Are there any other questions?
Hello. Yeah. So I was just picking up on a point in the summary slide. So you mentioned obviously that this log-normal distribution for ice-induced fragmentation presents some quite compelling evidence regarding wave breakup of flows. But I was just wondering kind of what the case was for other forms of fragmentation. Just like, so for example, I think there's 2015 paper from Garadi and Legomarcino that kind of looked at some FSD data, and in particular, they kind of described like idealized models of brittle fracture, of in-plane brittle fracture would show, like not of necessarily sea ice, but an idealized brittle system that would show the emergent distribution would be like, of this idea that the fragment size distribution would be like a parallel with this fixed exponent, so with an upper cutoff. So I'm just wondering if you kind of have a different perspective on kind of other forms of fragmentation, moving away from wave breakup of sea ice.
Yeah, so my understanding, sorry, I'm not sure I fully understood the question. It was kind of hard to hear, but my understanding, so from, I'm not an expert at all in fragmentation theory and just the fracture mechanic in general. But my understanding is that there are basically roughly two types of fragmentations. So there's this, what is instantaneous fragmentation? So when there's a lot of fragments created at the same time. And so that's what I mentioned earlier, because there's some evidence that it's well modeled by a tapered power law. So that would happen for very small flow sizes. But then there is a continuous fragmentation, which is when you have this, sorry, something fell here. So when you have this much slower and repeated fragmentations, multiple events, and yeah, there's multiple ways of looking at that. So there was the way which leads to scale invariance, which I mentioned earlier. There was this Karmograph theory, which leads to log normal, but there are even other ways of doing that. It's absolutely not the only way. So clearly here, I chose that because that was consistent with what our simulations was doing. So I'm not sure I answered your question, but yeah.
Thank you. Are there any other questions? We've time for one more, if anyone has one. Okay, we'll move to the next speaker, but while we're doing that, I'd just like to mention the paper that Fabien mentioned in his talk. Montiel and Squire had a system for breaking circular flows into circular flows, which had me mind-boggled for quite a long time. So each large circular flow created smaller circular flows. So it's a very special kind of breakup that is even more complicated than Danny's.
That was quite an achievement, yeah. All right, thank you.
You got that? Yep.